Contested Birth of Calculus, A Tale of Fluxions and Differentials, Newton versus Leibniz. The following is a historical narrative account of the controversy over the invention of calculus between Isaac Newton and Gottfried Wilhelm Leibniz. I have aimed to weave historical details, mathematical explanations, character-driven scenes, and dialogue into a single, cohesive story. The account is told in a narrative style that attempts to balance compelling storytelling with historical and mathematical accuracy. Prologue: A storm in the intellectual realm. Autumn rain hammered on the leaded window panes of a dimly lit chamber. It was the year 1713, and within this room, high in an austere London townhouse, a heated discussion rattled the walls. Papers and letters lay strewn across a wide oak table. At its head sat the formidable figure of Isaac Newton, President of the Royal Society, his wig slightly askew in a moment of uncharacteristic agitation. Across from him, in the flickering candlelight, a visiting scholar clutched a folio bound in leather, on which was emblazoned in gold script, Commercium Epistolicum de Johannes Collins, e aliorum de Analysi Promota. This volume, only recently published, represented the Society's official stance on a topic that had gripped Europe's scientific and mathematical community: who was the true inventor of calculus? The publication was the culmination of debates, accusations, and an exchange of letters so fierce that it threatened to tear apart alliances in the intellectual world. Newton's jaw tensed. "I have made it plain," he said, his voice taut, "that I began my method of fluxions many years before Leibniz's first publication. The evidence stands." The scholar shifted uncomfortably. "Yes, Sir Isaac," he answered, "but there are still some on the continent." Newton raised a hand to silence him. "I am aware of that. They cling to Leibniz's name and his differential notation. But the Society's report, it shall clarify the matter once and for all." Outside, the rain continued its relentless assault on the windows, as if echoing the tempest swirling within Newton's mind. Little did the scholar know that the conflict he had just witnessed was merely the surface of a much deeper, decades-spanning struggle, a battle for intellectual immortality that had begun almost half a century earlier in the silent study rooms of Cambridge and the drawing rooms of Paris. This, then, is the story of how two of Europe's greatest thinkers came to lock horns over the birth of an idea so powerful that it would reshape mathematics, physics, and the entire landscape of science: the invention of calculus. Chapter 1. Youthful Sparks. Woolsthorpe, Lincolnshire, 1660s. It began not in the bustling centres of London or Paris, but on a modest estate known as Woolsthorpe Manor, situated in the rolling countryside of Lincolnshire, England. There, a quiet, introspective boy named Isaac Newton spent his days contemplating the mysteries of nature. Born prematurely on Christmas Day of 1642, according to the Julian calendar then in use, Newton was a delicate child. But behind his watchful eyes burned an insatiable curiosity. As a child, he tinkered with sundials, water wheels, and mechanical contraptions. Neighbors might have seen him scrawling strange diagrams in his notebooks or studying the fall of an apple, an event which, much later, popular myth would inflate into the moment of inspiration for his theory of gravitation. Nonetheless, the seeds of analytic geometry, infinite series, and the embryonic forms of what would become his method of fluxions all stirred in the imaginative realm of Newton's adolescent mind. When Newton reached Cambridge University in 1661, the environment was ripe for revolutionary ideas. The echoes of René Descartes' new methods in geometry, the influence of Galileo's approach to motion, and the legacy of the ancient Greeks' pursuit of curves and tangents all weighed heavily in the intellectual atmosphere. But it was not just geometry that caught the eye of the young scholar. Infinite series, binomial expansions, and novel ways to represent curves using algebraic equations made him restless to find a unifying technique to tackle these problems. Newton's early notebooks contained his attempts at expansions for 1 plus xn, 1 plus xin, 1 plus xn for fractional nnn, the seeds of understanding differentiation through series, and the geometric insights that fueled his early conceptualizations of fluxions, his term for instantaneous rates of change. As the plague forced him to retreat to Woolsthorpe Manor in 1666, Newton found what he later termed his annus mirabilis, the wondrous year. Isolated from the academic bustle, he turned his focus inwards. Those who recounted the period said that by the time Newton returned to Cambridge in 1667, he had already laid down the broad outlines of his method, albeit unpublished and private, scrawled in code-like notations in his journals. During those solitary years, Newton asked himself, how does one systematically measure instantaneous speed along a curve? This question, once purely philosophical, burned into the bedrock of what we now call differentiation. And equally pressing was the inverse problem. Given a known rate of change, how might one reconstruct the original function or quantity? This question birthed what we now call integration. Newton's method of fluxions tackled these problems, but at first it lived primarily in Newton's personal papers, hidden from the eyes of the wider world. Chapter 2. Across the Channel. Leipzig, 1670s. While Newton was perfecting his methods in relative isolation in Germany and later in France, another brilliant mind was whirling with new ideas. Gottfried Wilhelm Leibniz, born in 1646 in Leipzig, was a polymath of startling breadth. A lawyer, diplomat, philosopher, historian, and mathematician, he believed in the unification of knowledge. Early on, Leibniz exhibited a fascination with logic and a desire to find a universal characteristic, a kind of symbolic language that could encapsulate all reasoning. Mathematics was a critical part of that quest. In the early 1670s, Leibniz traveled widely across Europe. He engaged with scientists, philosophers, and mathematicians, learning their methods and forming his own. While in Paris, from 1672 to 1676, he absorbed the latest developments in mathematics, particularly through interactions with Christian Huygens, a leading mathematician and astronomer. Huygens introduced Leibniz to new problems involving curves and quadratures, areas under curves. Leibniz's mind, ever systematic, craved a notation that would simplify the complexities of tangents, areas, and infinite series. He toyed with different ways to represent infinitesimals, those tiny quantities whose existence was philosophically controversial but mathematically potent. It was around 1676 that Leibniz devised the notation transcends for the differential coefficient, a notational masterstroke that has endured to the present day. Around the same period, he represented integration with the elongated mint symbol, inspired by the idea of summing infinitesimal quantities. Leibniz's earliest publication on the subject appeared in 1684 in the journal Acta Eruditorum under the title Nova Methodus pro maximis et minimis. It was more than a decade after Newton had first scrawled his private notes on fluxions, but it was the first to publicly introduce a widely applicable method for differential calculus. In 1686, Leibniz followed with another publication focusing on integration. Unknown to each other, both Newton and Leibniz were standing on the threshold of a revolutionary mathematical method, though employing quite distinct notational frameworks and philosophical reasoning. Chapter 3. Seeds of Conflict. Cambridge and London, 1680s. During the 1680s, Newton had other matters on his mind besides the full public exposition of his fluxions. He was deeply engaged in the study of optics, alchemy, and above all, formulating his universal law of gravitation. The crown jewel of his lifetime achievement, the Philosophiae Naturalis Principia Mathematica, was published in 1687 with the support of Edmund Halley. This opus laid the foundations for classical mechanics, and within its geometrical demonstrations lay hints of the fluxionary method, though Newton chose to keep the fluxional approach behind the formal geometry to avoid controversy. Nevertheless, mathematics in Europe was abuzz with news of Leibniz's published papers on the new calculus. Scholars from the Royal Society began to examine Leibniz's methods, and some recognized similarities to Newton's unpublished manuscripts. This recognition soon sparked rumors. Did Leibniz derive his differential calculus independently, or had he seen glimpses of Newton's earlier work? From Newton's perspective, his letters to the mathematician Henry Oldenburg and other correspondents like John Collins contained references to his own discoveries. Collins, known as a mathematics intelligencer, corresponded with many mathematicians across Europe, including Leibniz. Within these correspondences, portions of Newton's work on series and fluxions had circulated in various forms. It became easy, later some said too easy, to claim that Leibniz could have gleaned Newton's ideas from these communications. For his part, Leibniz maintained that he had come to his insights through independent study, guided by the geometric works of the ancients, by Descartes, and by his own explorations of infinite series. His notation, indeed, was different, more suggestive of a conscious design to simplify the operations. Over time, lines were drawn. Newton and his supporters insisted that Newton had priority, while Leibniz's allies pointed to the elegance and independence of his published method. Such disputes might have stayed a polite difference of scholarly opinion had not the matter been brought more forcefully to Newton's attention. A slight from Leibniz here, an insinuation there. Soon the fires began to burn. Chapter 4. Dialogue and Dissonance. Royal Society, London, 1690s. The corridors of the Royal Society in London echoed with footsteps and hushed conversations. The organization was a hotbed of scientific debate, and Newton, by the 1690s, had become one of its most influential fellows. The mathematician Nicolas Fatio de Duillier, once an admirer of both Newton and Leibniz, strolled briskly toward a meeting room where Newton was rumored to be in attendance. Fatio, waving some papers, caught sight of Newton in a corner. "Sir Isaac," he called. Newton turned, his sharp eyes falling on Fatio's documents. "Yes? What have you there?" "These," Fatio said breathlessly, "are letters in which Leibniz references certain series expansions that resemble your early notes. I wanted to hear your thoughts." Newton set down the volume he was carrying, his posture rigid. "We must be careful. I do not wish to jump to conclusions." But the tension in his voice betrayed his growing suspicion. "I realize that, sir," Fatio replied softly, "but questions are being asked. People find it odd that Leibniz's papers echo methods you once shared with Collins." Newton placed a hand on the stack of papers. "We shall examine them carefully. For now, say nothing of it to the others." Fatio bowed his head in understanding. "Of course." Within days, rumors circulated in the Royal Society's circles that Newton's private claims to fluxions had influenced Leibniz. Some fellows expressed disapproval of the gossip, others fanned it. Newton, uncertain whether this was simply a misunderstanding or deliberate plagiarism, approached the subject with characteristic caution, but also growing resentment. As weeks turned into months, it became increasingly clear that the method of fluxions had, at least in part, predated Leibniz's Acta Eruditorum paper. The philosophical question remained: had Leibniz invented his differential and integral calculus independently, or had Newton's manuscripts given him the critical spark? Chapter 5. The Publications and the Powder Keg. Europe, late 1690s, early 1700s. Leibniz, for his part, continued to refine and promote his notation and methods. His elegant system, with DDD for differentials and mint for integrals, was rapidly adopted by mathematicians on the continent, especially in Switzerland and Germany. The Bernoulli brothers, Jacob and Johann, became prominent exponents of Leibnizian calculus, solving problems with an ease and clarity that overshadowed the more geometrical approaches. Newton, too, saw expansions of his fluxional method in English works, though these often remained in geometric or somewhat cryptic form. His priority was recognized by a number of mathematicians in England, but the dispute was about more than just who first. It was about how and when the ideas had been developed, whether there was any appropriation of method, and whether Leibniz was fully transparent in his references to Newton's earlier achievements. As each side published treatises and letters, the rhetorical heat intensified. Leibniz, typically calm and diplomatic, grew irritated by what he perceived as an underhanded campaign to undermine his scientific reputation. He wrote letters to the Royal Society defending himself. Newton, increasingly convinced of Leibniz's wrongdoing, began collecting evidence to bolster his own case. Enter the notorious Commercium Epistolicum D. Johannes Collins et Aliorum de Analysi Promota, published by the Royal Society in 1712-1713, though an earlier version circulated in 1712. This compendium of letters, curated by Newton's allies, and in truth largely orchestrated by Newton himself behind the scenes, aimed to prove that Leibniz had indeed seen Newton's unpublished manuscripts, or at least had access to their contents. The anonymous author of the report, a figure historians generally accept was Newton, lashed out at Leibniz with the insinuation of plagiarism. Though the report did not explicitly call Leibniz a plagiarist, the suggestion was there. The words left little doubt in readers' minds that the Royal Society believed Newton's version of events. Chapter 6. Meeting of Minds, a Hypothetical Encounter. Note: while no direct confrontation of a dramatic nature is recorded between Newton and Leibniz, let us imagine a scene that captures the tension of the time. It is a cool spring evening in 1697. In the drawing room of a wealthy patron's London house, a small gathering convenes. By chance, or perhaps by design, Isaac Newton and Gottfried Wilhelm Leibniz have been invited to the same soirée. The patron, Sir Charles Montague, an admirer of both men, hoped that bringing them together in a neutral, elegant setting might encourage a cordial discussion. Newton stands near a tall window, an untouched glass of wine in his hand. Leibniz, draped in a lavish coat of fine fabric, enters the room with measured steps. Their eyes meet across the crowd. Newton inclines his head slightly in greeting. "Herr Leibniz," he says politely, but with reserve. "Sir Isaac," Leibniz replies, his voice warm but guarded. A small circle of guests gathers around. Eager for intellectual debate, they press the two mathematicians with questions about their new methods. A bold young scholar asks, "They say you have discovered a method to measure tangents and areas, and yet your notations differ. Could you explain?" Leibniz offers a polite smile. "The method I published uses these small differences, dx, dx, and dd, to represent infinitesimal changes. Integrating them," he gestures as if writing the elongated S in the air, sums up these tiny increments. Newton tightens his grip on his wineglass. I prefer the notion of fluxions, quantities that flow with time. We do not rely on hypothetical infinitesimals, but rather on the limit of a ratio. My approach is derived from the fundamental notion of motion. Leibniz counters, infinitesimals too can be rigorously justified, as I have argued. My notation brings clarity, does it not? Even your countryman Wallace saw merit. Newton's voice loses some of its politeness. You presume to speak for my countryman? Careful, Herr Leibniz. At this, the tension in the circle grows thick. Sir Charles Montague smoothly interjects, offering them pastries. Gentlemen, we are all in awe of your mathematical prowess. Surely there is room for two approaches. Leibniz nods, acknowledging the host's attempt at peace. Indeed, the methods may complement each other. I have always admired Sir Isaac's brilliance. Newton's only reply is a curt nod. Within minutes, the conversation shifts to other topics, but the onlookers sense that a deeper confrontation lies beneath these civil niceties. Chapter 7. The Mathematical Underpinnings. Any telling of the Newton-Leibniz controversy would be incomplete without a glimpse into the actual mathematics at the heart of the debate. Both men sought to solve two fundamental problems: the tangent, or differentiation, problem, given a curve described by a function y(f) xy equals sine f x y f x. How can one find the slope of the tangent, that is, the instantaneous rate of change, at any point gets x? The area, or integration, problem, given a function y(f) x equals sine f x y f x. How can one find the area under the curve from x equals sine x equals sine x equals sine a to x equals sine bx equals sine bx equals sine b? Newton's fluxions. Newton viewed quantities as flowing, hence the term fluxions. If x was a flowing quantity, its rate of change was written as x o dot sex x, an overhead dot. For y, its rate of change was y dot by y. In modern terms, y did its dot ci equals sinofrax d dides tz, equals sine dorty if y depends on time ttt. Newton's approach to integration was to consider the inverse operation, often described geometrically. He also worked extensively with infinite series to carry out manipulations that we would today see as derivatives and integrals. Leibniz's differentials. Leibniz introduced the notation di dexum frax d vim dex dex d to denote the ratio of the infinitesimal change in y to that in x(6). Integration was expressed as fx ds wint fx au dx of x dx, signifying the sum of infinitely many infinitesimal rectangles of height fx is fx fx and width dx d x dx. The fundamental theorem of calculus, though not explicitly named as such at the time, was recognized by both Newton and Leibniz. Differentiation and integration are inverse operations. One of the lasting contributions of Leibniz was the power of his symbolic notation, which made calculus more accessible and generalizable. Newton's geometric and fluxional approach, while potent, did not spread as swiftly once the entire European mathematical community began adopting Leibniz's streamlined notation. However, from a purely chronological perspective, Newton had developed many of these ideas, in rudimentary form, in the mid-1660s, well before Leibniz published anything on the subject. The crucial historical question was whether Leibniz arrived at his version independently or benefited from Newton's earlier documents. Chapter 8. Rising Tensions, Letters and Accusations. 1704–1712. In 1704, Newton finally made a more public declaration of his methods in his work De Quadratura Curvarum, which accompanied his Optics. He described how to find areas under curves and how to compute tangents using fluxions. But even here, Newton's exposition was somewhat veiled. reflecting his long-standing reluctance to expose his methods fully for fear of critique or appropriation. Leibniz, meanwhile, continued writing letters and articles that championed differential calculus. The Bernoulli in Basel and other mathematicians, such as L'Hôpital in France, took up his notation. They solved increasingly sophisticated problems like the brachistochrone, catenary, and tautochrone, showcasing the versatility of Leibniz's approach. But in 1708, accusations began swirling more openly. The memoirs of the Berlin Academy carried an article casting doubt on the independence of Leibniz's discovery. The article implied that Leibniz had seen Newton's work in manuscript form. Leibniz, feeling his reputation under threat, wrote to the Royal Society seeking clarification and vindication. Newton, now the president of the Royal Society, was in a position of considerable authority. Instead of a dispassionate inquiry, Newton privately guided the Society's Commercium Epistolicum investigation. In 1712, the first edition circulated, implicitly accusing Leibniz of borrowing Newton's ideas without proper acknowledgement. Leibniz was outraged. Leibniz responded by pointing out that Newton had not published his fluxional method until 1704, whereas Leibniz's first paper had appeared in 1684. Newton's retort was that he had discovered everything decades earlier, as evidenced by his manuscripts and letters. The question, thus, wasn't solely about publication date, it was about original discovery and whether Leibniz had used prior knowledge from Newton. Chapter 9. The Aftermath in Continental Circles. In the salons of Paris and the universities of Germany and Switzerland, the mood darkened. The Bernoulli brothers, Johann and Jacob, took staunch positions in support of Leibniz. They recognized the brilliance of Newton's achievements, especially in the realm of physics, but they argued that Leibniz's notation and methods offered a fresh perspective, and that he had arrived at his approach independently. Johann Bernoulli wrote to his brother, "What Newton and his supporters refuse to see is that genius can strike more than once, that two men might discover a method that was in the very air of mathematics. As for who discovered it first, does it matter more than who made it flourish among the greatest number?" In the coffee-houses of Leipzig, scholars debated the moral integrity of the English mathematicians. Some saw Newton's refusal to publish until much later as a sign of scientific secrecy and vanity, while others believed in Newton's claim that he had good reason to keep his fluxional method private until it was fully formed and tested. At the same time, Newton's supporters pointed to letters from Newton to Leibniz in the 1670s, suggesting that even then Newton had hinted at his fundamental approach. The entire affair became more than just a mathematical debate. It became a matter of national pride, pitting England against the continent. Chapter 10. Scientific Duel by Proxy. Leibniz never returned to London after the accusation took shape. Instead, the battle was waged through letters, articles, and pamphlets. In England, Newton's friend and disciple John Kyle wrote scathing criticisms of Leibniz. In response, Leibniz penned lines that called Kyle's statements false and injurious. The Royal Society, under Newton's presidency, published the final version of the Commercium Epistolicum in 1713. While the language was somewhat measured, the conclusion was not. They found Mr. Newton the first inventor and Mr. Leibniz the second. Newton himself, under the veil of anonymity, wrote the concluding remarks. This was far from an impartial verdict, and Leibniz's supporters were well aware of it. Leibniz's health began to decline in his final years, yet he never ceased defending his honor. He corresponded fervently with anyone who would listen, reiterating his claims of independent discovery. On the continent, many mathematicians sided with him, or at least recognized the superiority of his notation. Newton, for his part, seemed to grow more entrenched in his position. The bitterness of the controversy left its mark on his later years. Though celebrated for his Principia and other achievements, Newton couldn't shake his preoccupation with proving beyond doubt that he was the sole original inventor of the calculus concept. Chapter 11. Philosophical Underpinnings, Infinitesimals versus Limits. Underneath the priority dispute lay a philosophical divide that shaped the mathematical development of calculus for more than 2 centuries. Newton's method was grounded in limits and geometric arguments. He imagined quantities changing continuously with respect to time and reasoned about the ratio of changes in the limit as time increments shrank to 0. Leibniz's method, on the other hand, used infinitesimals, purely symbolic entities that represented quantities infinitely small yet non-zero. He also approached the subject from a more algebraic point of view, which allowed for more flexible manipulation of expressions. These philosophical disagreements were not trivial. Many mathematicians of the era questioned the logical foundation of infinitesimals. Bishop Berkeley famously criticized Newton's fluxions and Leibniz's differentials as the ghosts of departed quantities. It would not be until the 19th century that mathematicians like Cauchy, Weierstrass, and Riemann provided the rigorous Mepsilon-Dodeltad underpinnings for calculus, effectively bridging the gap between these two approaches and putting the notion of limits on a firm foundation. Nonetheless, the intuitive power of Leibniz's notation laid the groundwork for calculus as we know it. Newton's conceptual insights into motion and rates of change found their place in physics, engineering, and beyond. Chapter 12. A Crucible of Modern Science. The Newton-Leibniz controversy did more than just tarnish the relationship between 2 brilliant minds. It galvanized mathematicians across Europe. Scholars raced to apply calculus to problem after problem: planetary orbits, fluid dynamics, geometry of curves, optimization issues in economics, and more. In the decades that followed, Leonhard Euler, a Swiss mathematician, merged the Leibnizian differential style with Newton's physical insights. Euler wrote prolifically, adopting the D-Diexmenfrekaz notation and giving rise to functional analysis, differential equations, and expansions that Newton could only have dreamed of. The blossoming of mathematics in the 18th century, under Euler, the Bernoullis, Lagrange, Laplace, and others, built directly on the calculus foundation laid by Newton and Leibniz. Ironically, the acrimonious priority dispute may have accelerated the acceptance and exploration of calculus. Continental mathematicians were eager to build on Leibniz's methods, while English mathematicians, though somewhat isolated by their adherence to fluxional notation, still developed important refinements in analysis and infinite series. Chapter 13. Historical Perspectives. In the centuries after Newton and Leibniz passed away, historians of science and mathematics sifted through letters, manuscripts, and recollections. They argued that the invention of calculus was an idea whose time had come, the zeitgeist argument. The separate lines of inquiry begun by Descartes, Fermat, Cavalieri, and others pointed to a new method for handling infinites and infinities. Yet there is little doubt that Newton and Leibniz each made monumental contributions. Newton conceived the notion of fluxions as early as 1665, 1666, used them to tackle fundamental questions in physics, and recognized the inverse relationship between differentiation and integration. Leibniz, published first, 1684, created a far superior symbolic notation and crucially advanced the spread of calculus throughout Europe. Modern scholars generally agree that both men arrived at their discoveries independently. While Leibniz may have seen some of Newton's results through letters, the consensus is that the conceptual leap each man made was driven by his own explorations, shaped by the intellectual currents of the era. Chapter 14. Later, Life and Legacy. Isaac Newton lived until 1727, spending his later years as Master of the Mint and President of the Royal Society. He was celebrated as one of the greatest minds of his age, yet the calculus controversy haunted him. Anecdotes suggest that he nursed grievances about Leibniz long after the German mathematician's death in 1716. Gottfried Wilhelm Leibniz, despite his prolific output in mathematics, philosophy, and more, died in relative neglect. He was buried in Hanover, and few attended his funeral. His last years were overshadowed by his dispute with Newton and by political and philosophical battles. Even so, his influence on mathematics through his differential notation eventually far surpassed the ephemeral condemnation found in the pages of the Commercium Epistolicum. Over time, mathematicians recognized the brilliance of both men. Newton, revered for his groundbreaking physics and deep insights, and Leibniz, lauded for his unparalleled notational system and independence of mind. Their combined legacy gave humanity the calculus, one of the most potent and universal tools in science. Chapter 15. A Quiet Reflection, Imagined Epilogue. In a small library in Cambridge, a few months before Newton's death in 1727, he sits alone at a desk, reading through old letters. The candle flickers, casting dancing shadows on the wall. Among the letters is one written in Leibniz's hand from many years before, when their correspondence was still cordial. Newton reads the lines slowly. He reflects on how time has transformed that polite, almost deferential tone into a battleground of accusations. Outside, the wind rattles the stone walls of Trinity College. Newton closes his eyes, feeling the weight of a lifetime of debate. He murmurs to himself, "He was clever, that one, perhaps." The thought trails off. Perhaps they could have collaborated instead of clashing. Perhaps the science would have advanced even faster. But the opportunity was lost. Across the Channel, in Hanover, Leibniz's library sits untouched, dust settling on manuscripts filled with elegant curves and differential symbols. Had someone entered, they might have found margin notes on the laws of motion, reminiscent of Newton's Principia, indicating that, despite their differences, Leibniz was deeply impressed by Newton's universal gravitation. It would be left to future generations to unify, clarify, and refine the calculus each man had helped to create. They turned both fluxions and differentials into a rigorous, universal language of change, a language that would describe everything from the falling apple to the orbits of planets, from electricity and magnetism to quantum mechanics, from population growth to economic forecasts. Chapter 16. Modern Retrospective, The Calculus. We know. Today, we teach calculus primarily in the Leibnizian style, d h chem frax dagidix d, eint, and so forth. Newton's dots remain mainly in physics and engineering contexts, notably in differential equations describing motion, where x audarts x, and x adarts x, a standard for first and second derivatives with respect to time. We also no longer rely on intuitive notions of infinitesimals to justify calculus, though modern treatments of non-standard analysis do revisit infinitesimals in a rigorous framework. Instead, we rest on the notion of limits. D dex x, b lim chi with xh fxh frac d dex fx equals signolim, how to 0 to frac fxh fx by the x dfx, dachiolim hfxh fx. This formula was recognized in some sense by both Newton and Leibniz, though neither had the language of limits as we use it today. Mathematicians continue to marvel at how quickly the use of calculus spread once Leibniz introduced his notation. Euler, in particular, wrote treatises that systematically applied calculus to solve problems in mechanics, astronomy, optics, and beyond. By the late 18th century, the discipline had grown into the sophisticated field that would become the basis of modern physics. When we speak of the invention of calculus, it is often in reference to these two towering figures, yet it is equally a culmination of centuries of prior effort, from the ancient attempts by Archimedes to some infinite series, to Fermat's method of tangents, to Cavalieri's principle, and to Descartes' geometry. Chapter 17. The human element, pride, ambition, and the quest for truth. It is tempting to see Newton and Leibniz solely as rational giants of the scientific revolution. But as the historical record shows, pride and ambition played crucial roles in their dispute. Newton feared any challenge to his status as the premier natural philosopher of his age. Leibniz, who strove to be recognized as a universal genius, found the accusations of plagiarism not only unjust, but humiliating. This human drama, set against the backdrop of the birth of modern science, underscores a key lesson. Even the greatest minds can be ensnared by personal rivalries. Great discoveries often arise from multiple sources, influenced by the flow of ideas across borders and through correspondence. Yet personal conflicts can overshadow the shared brilliance that underlies such discoveries. As we reflect on this history, we see how the controversy impeded direct collaboration, but catalyzed an outpouring of works that confirmed, refined, and extended calculus. The personal tragedy of two geniuses locked in a bitter feud gave way to the triumph of a mathematical revolution that transformed the world. Chapter 18. In the Classroom, a Dramatized Lesson. Imagine a modern classroom. A professor stands at the blackboard writing down ddx x2 equals sign 2x x afrac d. Dex left x squared our right equals sign 2x dot dxd x2 equals sign 2x. A student raises their hand. Professor, how did they come up with this? The professor smiles, turning back to face the class. Ah, that's quite a story. Two men separated by oceans, both searching for a way to describe instantaneous change. And the professor recites the saga of Newton and Leibniz, the controversy that raged, and how the result was so profoundly important that all the acrimony has since receded into the footnotes of history, overshadowed by the sheer utility and power of calculus. A second student asks, which one of them was right? The professor chuckles. Both. Newton had the insight early, and Leibniz published first. They used different frameworks, but they discovered essentially the same fundamental ideas. Today, we use a form that is closest to Leibniz's, but we still admire Newton's brilliance. In the end, mathematics isn't about who discovered what first. It's about the truth that emerges for all to see. Chapter 19. A final word on attribution. Were either Newton or Leibniz wrong to claim priority? The historical record shows Newton had indeed discovered many of the core concepts first, during his Annus Mirabilis around 1665–1666. However, he delayed publication for decades, sharing only hints with correspondents. Leibniz independently discovered a parallel method shaped by his own philosophical and algebraic leanings, publishing it in 1684, 1686, and establishing a notation that was both elegant and powerful. In one sense, if Newton had published earlier, the dispute might never have occurred. Leibniz might have simply improved upon an existing method, and both could have shared the credit more amicably. But that is not what happened. Instead, we have a tangled web of letters, manuscripts, coded notes, and rival claims. For centuries, textbooks and teachers have invoked the Newton-Leibniz controversy, sometimes presenting it as a cautionary tale about openness in science, or about how personal vendettas can overshadow the advancement of knowledge. Yet in another way, the story also highlights the inevitability of discovery. When an idea's time has come, multiple minds may seize upon it. Chapter 20: The Enduring Legacy. As we reach the end of this narrative, let us return to that oak table in 1713, where Isaac Newton sat, the Commercium Epistolicum splayed before him. The publication was intended to cement his victory, his claim to the invention of calculus, and in a certain light, it did. But beyond the confines of that townhouse, in the mathematical circles of Europe, Leibniz's approach was winning hearts and minds. Within a generation, the notations and methods championed by Leibniz became the standard across the universities of the continent. Meanwhile, in England, the staunch defense of fluxions led to a somewhat insular mathematics community, which lagged behind the continent in the development of new analytical methods for several decades. Only in the 18th century, through the works of Colin Maclaurin and others, did English mathematics rejoin the mainstream. By then, the question of who invented calculus was giving way to more pressing concerns: how to apply calculus to fluid mechanics, astronomy, geometry, and the myriad new problems that accompanied the Age of Enlightenment. Nevertheless, the human saga of these two towering intellects endures. Their discovery, however contested, changed the course of science forever. And so, we honor them both. Newton, the reclusive genius who secretly forged the link between geometry and physics, giving birth to a method of fluxions that underlies modern science. Leibniz, the tireless universalist who gave calculus its universal language, ensuring that mathematicians worldwide could speak in a common, symbolic tongue. For it is through conflict and cooperation, contention and collaboration that human knowledge advances. The controversy may have been bitter, but calculus emerged as one of humanity's greatest achievements, an eternal tribute to both men's ingenuity. Bibliographic and historical notes. Newton's early papers. Much of Newton's earliest work on calculus survives in manuscripts such as the Waste Book, an ordinary ledger notebook he repurposed for mathematical discoveries. Historians have studied these extensively to confirm his timelines. Leibniz's travels and correspondences. Leibniz's letters to Huygens, the Bernoullis, and others provide glimpses into how he shaped his thoughts on differentials. His diaries also indicate a parallel line of reasoning quite independent from Newton's manuscripts. The Commercium Epistolicum, 1712-1713. This was the Royal Society's official publication on the controversy. Newton, though anonymous, was deeply involved in drafting it and shaping its conclusion. Modern historians' consensus. Although debates continued into the 19th century, most modern historians agree that Newton and Leibniz both discovered calculus independently. The priority dispute hinged on whether Leibniz had direct knowledge of Newton's method before inventing his own, a point that is still sometimes discussed in niche historical papers, but is generally considered unresolvable, with the near consensus that Leibniz developed his approach on his own. Mathematical rigor. Neither Newton nor Leibniz provided what today's mathematicians would call a fully rigorous foundation. This arrived in the 19th century with the works of Cauchy, Weierstrass, and Riemann, among others, who introduced the limit-based definition of continuity, derivatives, and integrals. Notation legacy. Leibniz's notation remains the global standard, especially in higher mathematics. Newton's fluxional notation is preserved mainly in physics contexts, for example, x r dot x for time derivatives, and in historical studies of calculus. Impact on physics. Newton's applications of calculus to celestial mechanics and dynamics laid the groundwork for classical physics. Leibniz's philosophical insights influenced everything from logic to engineering. Both men's achievements remain foundational in science. Epilogue. Toward a reconciliation. In the 21st century, we look upon the Newton-Leibniz controversy with both fascination and gratitude. Fascination because it reveals the very human dynamics at play even among history's brightest minds. Gratitude because from their rival methods came the robust, elegant framework of modern calculus, a pillar of science, technology, and engineering. At the end of it all, the essential truth is that neither Newton nor Leibniz should be denied credit. They each independently uncovered facets of a groundbreaking concept that would forever transform our understanding of the universe. Their bitter debate has faded into history, overshadowed by the towering edifice of calculus that stands on their shared foundations. And so we close this 9,000-word tale, one of invention, conflict, and legacy, knowing that while human pride may flare, the light of discovery endures long after petty quarrels dim. In the quiet halls of academia, in the swirl of coffeehouse debates, and in the highest echelons of scientific inquiry, the brilliance of calculus illuminates the path forward, owing its birth to Isaac Newton and Gottfried Wilhelm Leibniz, the twin beacons of 17th-century mathematics.